Welcome to the 23rd lecture on calculus. Today we will discuss the notion of continuity of functions of single variables. We will see some properties of continuous functions also along with examples. So first let me recall what is open and closed intervals. So you consider two real numbers a and b such that a is less than b, then an open interval, it is denoted in this way, so b, and it is just collection of all those real numbers x such that a is less than x less than b. And closed interval, it is denoted in this way, so a comma b square bracket, and it is just collection of all real numbers x such that a less than or equal to x less than or equal to b. And what is continuous function? So you consider a function like this, it is whose domain is this open interval, or it can be a function whose domain is this closed interval. So a function like this or like this, it is called a continuous function if its graph does not have any breaks. And what is the graph of a function? So if you consider this closed interval, you collect all the points in this closed interval, and suppose it is c, then its corresponding corresponding function value f of c, that will be somewhere here. So if you collect all the function values for each point in this closed interval, then you will get the graph of this function, and it is like this. And a function, it is called continuous function if its graph does not have any break. So this function, this graph, it does not have any break, while if you consider this function and its graph is suppose this one, so it has a break at this point, okay, at the point c it has a break. So this function, it is not continuous at this point, but it is continuous on this closed interval. Intuitively, continuous functions are functions whose graphs can be drawn on a paper without lifting the pencil. Okay, so this graph you can draw on a paper without lifting the pencil. So this function is continuous on this closed interval, while this graph, it cannot be drawn on a paper without lifting the pencil. So you have to lift the pencil at this point. Okay, so that is why this function, it is not continuous at this point. Okay. A rigorous definition of continuity of real functions is usually given using the notion of limits. So you consider a point c in this closed interval, then the function f is said to be continuous at the point c if this function value f of x approaches to this function value f of c as x approaches to the point c. So this is the definition of a continuous function at this point c in terms of the notion of limits. So here we give the rigorous definition. So you consider a point c in this closed interval, and you consider a function from this closed interval to the set of real numbers, then this is called a continuous function at the point c. So if limit of this function f of x at x equal to c exists, and this limit, it is same as this function value f of c. Okay, so what I mean, so equivalently this thing, it is same as that both left and right hand limits should exist at the point c, and this left hand limit and right hand limit both should be same as this function value. Okay, so if you consider this point c, so this function, it is continuous at this point. Why? Because so its left hand limit, so if you approach to c from the left side, you will get this left hand limit. In this case, you can see that left hand limit exists, and similarly right hand limit also exists at x equal to c. So it will come along this way. So and both are same as this function value f of c. Okay, while if you consider this function, so this is the graph, and let's analyze whether this function is continuous at the point x equal to c. So though its left hand limit and right hand limit exist, but it is not continuous at c. Why? Because if from the left side you will get left hand limit, so that will be this value L1, and if you approach to c from the right side, you will get right hand limit, so it is same as L2. So in this case, left hand limit, it is not same as the right hand limit. Okay, and of course this function value, it is just f of c, and that is same as this right hand thing. So So up to this point, so it is open. Up to this point, this function value is given by this, and just from C onwards, this function value is given by this thing. So here you can see that both left hand limit and right hand limit exist, but they are not equal. Okay. So this function, it is not continuous at the point C. Okay. So let me recall it quickly. A function from this closed interval to R, it is called a continuous function at C if this limit exists and this is same as this function value. So this limit exists, it is equivalent to say that both left hand limit and right hand limit exist and these are equal. Okay, and then if you have this equality, it is basically saying that both are not only both are equal, but these are equal to this function value. Okay, so it is continuous at the point C if you have this thing, and it is equivalent to say that both left hand limit exist and right hand limit exist and both are same as this function value. Okay, when this C is one of the end points, so suppose C is A, so this is the first point in this closed interval, then even this notion, then also we can talk about continuity at the point C. Okay, and in that case this function, it is called continuous at the point A if, in this case, you just have to consider only right hand limit. Okay, so in that case, so we call f is continuous at A if right hand limit exists and right hand limit is same as this function value. Okay, so right hand limit should exist and that should be same as this function value f of A. And when C is B, that is the this point in this closed interval, then this function, it is called continuous at this point B if, in this case, left hand limit exists. So that means if you approach to B from the left side, this limit should exist. Okay, and that limit, that should be same as this function value f of B. Okay, so this is the notion of continuous function at a particular point C. Okay, and then if you recall the equivalent definitions of limits of functions, then this we can give these equivalent definitions for continuous function at a particular point C. So again, you consider this point, this a point in this closed interval, and this a function from this closed interval to the set of real numbers, and this function is continuous at the point C by definition if this limit exists and it is same as f of C. And then you recall the equivalent definitions of limits. Okay, so it is done in lecture 19. Okay, so this limit exists and it is same as f of C. It is equivalent to say that for every sequence x suffix n in this closed interval, if your sequence converges to C, then this function value f of xn, it should converge to f of C. So that is the definition of continuity of a function at the point C in terms of sequences of real numbers. Okay, so directly we can say that a function is continuous at the point C if for every sequence xn in this closed interval, and if that sequence converges to C, then this function value, it should converge to f of C. So this is one equivalent definition, and equivalently you have another definition. So it is epsilon delta definition. Okay, so this limit, it is same as f of C. It is by definition, in terms of epsilon delta definition, we can say that for every positive real number epsilon, there exists a positive real number delta, such that for all points in this closed interval, if x lies in the delta neighborhood of C, then this function value f of x, it should lie in the epsilon neighborhood of f of C. Okay, so f of C is the limit of this function at x equal to C. That means it should satisfy this epsilon delta condition. Okay, for every epsilon there should be some delta, such that for all points in this delta neighborhood of C, this function value, it should lie in the epsilon neighborhood of f of C. So these are two equivalent definitions one can have for a continuous function at this point C. Okay, a function f on the domain, this open interval, or domain can be this closed interval, or domain can be this set of real numbers, or domain can be anything else. So a function f on a domain, it is called a continuous function if f is continuous at every point in that domain. Okay, so if your domain is this open interval, f is called a continuous function on this domain if f is continuous at every point in this domain. Okay, if domain is this, then f should be continuous at every point here. And if domain is R, so suppose f is a function from R to R, then f is called continuous function. Okay, if it is continuous at every point C in R. Okay, so if f is not continuous at this point C, we say that f is discontinuous at C, or that point C, it is called a point of discontinuity for f. Okay, next we should see some examples. So here you consider this function whose domain is this collection of all non-zero real numbers, right? That for all negative values of x, f of x is same as -1, and for all positive values of x, f of x is 1. Okay, and now let's analyze whether this function is continuous or not. Okay, so if you consider a point C that is not equal to 0, so suppose C is somewhere here, then you can easily see that in this range, this function value it is given by this constant thing. So in this range it is actually same as this constant function f of x equal to 1. So one can easily prove that this function is continuous. Okay, and this limit, one can easily prove that at this point when c is not equal to 0, this limit exists and it is same as this function value. So the function f is continuous at every point c not equal to 0. So how to prove this? So since it is given by this constant thing, you consider any sequence, okay, in this interval which converges to c, then its function value f of xn, it is just giving this constant sequence. Okay, it should converge to 1. Okay, so using the definition in terms of sequences, one can prove that this limit exists and it is same as this function value when c is not equal to 0. So f is continuous at this point c not equal to 0. What about this point 0? So since this limit does not exist, we can conclude that this function is discontinuous at x equal to 0. And why this limit does not exist? That if you approach to 0 from the left side, then your function value it is approaching to -1. So in this case left hand limit is -1, but if you approach to 0 from the right side, you will get that right hand limit it is just 1. So left hand limit it is not same as right hand limit, therefore this limit does not exist. And you can conclude that your function f is discontinuous at x equal to 0. Okay, so what is the definition of continuous function at x equal to 0? That limit should exist and limit should be same as f of 0. But in this case limit does not exist. So you can conclude that f is discontinuous at x equal to 0. What about this function? So there is a function from this set of real numbers to itself, and if x is negative, then this function value is given by 1. At x equal to 0, this is 2, and if x is positive, then this function value is given by x plus 1. So this is the graph. Okay, so up to this thing it is given by this constant value y equal to 1, and at x equal to 0 it is just this value, and after 0, so it is given by this, the graph is this one. So in this case one can prove that this limit exists, because in this case both left hand limit, if you approach to 0 from the left side, you will get left hand limit that is just 1, and right hand limit, if you approach to 0 from the right side, right hand limit that is also 1, one can prove. So in this case left hand limit is same as right hand limit and both are same as 1, so therefore this limit exists and it is same as 1. So you have this one, but is it same as the function value? What is the function value at x equal to 0? So it is f of 0, it is just 2. So this limit it is not same as this function value, therefore this function f it is not continuous at x equal to 0. So f is discontinuous at x equal to 0. But if you consider x that is non-zero, then y not equal to 0, one can prove that limit of this function at c it exists and it is same as the function value f of c. So I will leave this thing as exercise. One can verify that f is continuous at every point c not equal to 0. Okay, and here we discuss the relations between continuous functions and algebraic operations. Okay, so this thing we have discussed already for limits, and using those results now one can argue that sum of two continuous function is continuous, and their subtraction, product, division all are continuous functions. So here is the theorem. You consider a point C in this closed interval, and suppose f and g are two functions, continuous functions at this point C. So both are functions from this closed interval to the set of real numbers, and both are continuous functions at this point C. Then what can you say about the continuity of the sum, subtraction, product, division, and this absolute value at the point C? So this theorem says that if f and g both are continuous at x equal to c, then their sum f plus g, that is also continuous at c. F minus g, that is also continuous at c. For any real number r, this function r times f, this is also continuous at c. And this product function, that is also continuous at c. And this division f by g, it is continuous at c, provided this g of c, that is non-zero. Okay, so in this case you need this extra condition. Okay, and this absolute value, so this the function given by this absolute value, that is also continuous at c. How do you prove f and g both are continuous at c? So by definition this limit exists and it is same as this function value, and this limit also exists and it is same as this function value. Okay. Then using the relations between limits and algebraic operations of functions, these are discussed in lecture 20. So one can get that limit of this sum of x at x equal to c, it is same as f plus g of c. Okay. So similarly one can prove that limit of this thing at x equal to c, it is same as the function value. So one can prove all the other statements. Okay. And here are some examples of continuous functions. So you just consider this identity function. So this is the function from the set of real numbers to itself, and f of x is defined to be x for all x. So this we call it identity function, and one can prove using one of those equivalent definitions. Either you can use the definition in terms of sequences, or you can use the epsilon delta definition. So one can prove that limit x tends to c, x, it is just c. Okay, so this function, it is continuous at every point of this set of real numbers. And if you consider constant function, so you consider a fixed real number, and here this g of x, it is defined to be a for all x belongs to R. So this is a constant function given by this constant. Okay. So this constant function one can verify that in this case also limit exists at every point, and that is same as a. So this function, it is continuous at every point. Okay. So using these two results and the previous theorem, one can prove that if your function is given by these polynomials, so this is a polynomial over this set of real numbers, then this function, it is continuous function, and that means it is continuous at every point of R. Okay. So how to prove that? So this function, it is actually combination of summation and product of continuous functions. So therefore this is a continuous function. Okay. What about a function given by these things? So you consider two polynomials over R. So one is p of x and another one is q of x. So here coefficients are real numbers. Okay. So that is why I am saying that these are polynomials over R. And then you define a function from the set of real numbers to itself, defined by this thing. Okay. So f of x, it is same as p of x by q of x. So if I should write is non-zero. Okay. So of course this domain is not whole thing. So here I should write, so this is a function from the domain D to R, and what is D? So this is just collection of all real numbers such that q of x is non-zero. So only for those points we can define this function, and this function value, it is given by this p of x by q of x. So we call such function as a rational function. And what about the continuity at a particular point C? So since these functions given by polynomials, these are continuous functions, and then you use this result that this f by g, it is continuous at C provided g of C is non-zero. So using that, one can conclude that this function, it is continuous at every point C such that q of C is non-zero. And here is another example. So in this case, your domain, this is just collection of all non-negative real numbers. Okay, so this is closed 0 and open infinity. Okay, this is just collection of all these real non-negative real numbers. And your function f from d to r, this is defined by f of x equal to square root of x. So we prove that this function is continuous on this domain D. So that means it is continuous at every point in the domain. Okay. So basically we need to prove that limit extends to C, f of x exists, and that is same as f of C. So here let's use epsilon delta definition to verify this thing. We should prove that this f of C, it satisfies epsilon delta condition for continuity, okay, for the limit. Okay. So first you analyze this distance. So this distance between f of x and f of C, that is just square root of x minus square root of C, its absolute value. And if you multiply both numerator and denominator by this thing, you will get that this is same as absolute value of x minus C and absolute value of this thing, square root of x plus square root of C. So then you can see that this value, it is less than or equal to this one, because in the denominator, if you just omit this term, so you are reducing the denominator, you will get some bigger value. Okay, so it is just this value, it is less than or equal to 1 by square root of C times absolute value of x minus C. And then one can easily verify epsilon delta condition. So you consider an arbitrary positive real number epsilon, and we should prove that for this epsilon there exists some positive real number delta which satisfies certain condition. Okay, so for this epsilon we choose our delta, that is epsilon times square root of C. So this is also positive real number. Okay, and in this case it satisfies this thing. So you consider any point from the domain, and suppose that point it lies in the delta neighborhood of C, then this function value f of x, it lies in the epsilon neighborhood of f of C. Why? Because if x minus C, so it is less than delta, and your delta is epsilon times square root of C, then from here you can get that 1 by square root of C x minus C, that is less than epsilon. And once this value is less than epsilon, and this thing, it is less than or equal to this thing, so this difference, this distance, it is also less than epsilon. Okay, so you have this thing. Okay, so thus for every epsilon we can have a delta depending on that epsilon, such that for all points in this delta neighborhood of C, this function value, it lies in the epsilon neighborhood of f of C. Okay, so we have that this limit, it is same as f of C, so f is continuous at x equal to C, and since C is arbitrary point in D, we can conclude that f is continuous at every point. Okay, so this function is continuous. And here is our last result in this lecture. So you consider two subsets A and B. So both are subsets of this set of real numbers, and suppose you have two functions, one is f from A to this set of real numbers, another one g, that is from B to this set of real numbers, such that f of A, that is contained in B. Okay, so image of f, that should lie in B, that is the condition. And then you consider a point from A. Suppose f is continuous at C and g is continuous at f of C. Okay, so then this composite function g compose f, so that is defined in this way. So g compose f of x, it is defined to be g of f of x. So this composite function, it is continuous at C. Okay. So how to prove that? We use the sequential criterion for continuity. Okay. So let me recall the definition first. So if you consider a sequence in the domain such that this sequence it converges to C, then your function value that should converge to the function value at C. Okay. We want to prove that this composite function is continuous at C. So we are considering a sequence which converges to C. Okay. And then you use your hypothesis. Your hypothesis is saying that f is continuous at C. So for this sequence which converges to C, so f of xn that should converge to f of C because f is continuous. And then you use this sequence and you use the fact that given hypothesis that g is continuous at f of C. So for any sequence which converges to f of C, this g of that sequence that should converge to g of f of C. Okay, because g is continuous at f of C. So you consider this sequence and you apply g. So you should get that g of f of xn that should converge to g of f of C. So ultimately you are getting that for any sequence which converges to C, then g compose f of xn it should converge to g compose f of C. Okay. So ultimately you are getting that this g compose f it is continuous at C. So it is satisfying the sequential criterion for continuity. Okay. So here is the corollary. The composition of any two continuous functions is continuous again. So suppose f is continuous on A and g is continuous on B, then this g compose f it is continuous on A. By this statement that a function is continuous on A, I mean that it is continuous at every point. So using this theorem you can easily have this corollary. And here is an example. So how we can use this theorem? So suppose we want to prove that this function h of x given by this square root of x square plus 5 for all x belongs to R, prove. Okay. So you consider this function and we want to prove that this function is continuous on R. Okay. How to prove that? So we just write this function as composition of two continuous functions. You set f of x, that is a function from the set of real numbers to itself. It is given by this thing. So f of x is x square plus 5, and you consider another function from the set of all non-negative real numbers to the set of real numbers. It is given by g of x, that is square root of x. And then what is h of x? It is just g compose f of x, right? So first you take f of x, then you will get this one, and then you apply g, you will get square root of this thing. Okay. So since both f and g are continuous, then this composition function h of x that is also continuous, and it is continuous at every point of the set of real numbers. Okay. So this is continuous that we have just proved, and this is the polynomial function, so it is continuous. Okay. So we have this example that this function is continuous at every point of R, set of real numbers.